Can you hear me?
Yes, Vita.
Yes.
Thanks, guys. So you can probably see my screen as well, I think, right?
Yes.
Thanks a lot. Okay, so this presentation is about introduction to the cStor replica. What is it actually, and what it may contain, and what is the thought process, the one which we are doing, and how it works. Very, very basic things, and for sure, one session is not sufficient to do an entire in a single. So we'll have like series of them, and yeah. So as Uma mentioned in the previous slide, like we have in the previous presentation, we have the pool concept, and then the volume concept, and then the target kind of thing. So here I'll start with the cStor pool, which is again the bunch of can consume a bunch of disk, can be anything on the host, or it can be somewhere in the remote, or SAN or S3. It can be any of them. So cStor cStor pool is like a container which will like having exposed or consumes these things, and tries to and does the whatever data it receives from the target writes into this disk. So that's how the very high level view of the cStor pool. Right? And then coming to the next is like we have called as the volumes. So again, as we saw in the previous presentation, we have the PVC is given, and then and the PV is created for the given PVC. Then basically on the back side, the background, we have the various pods gets deployed, and then various process will be started. Like so, here once the PVC is given, so the volumes will be created on this cStor pool, which is like which already consuming the bunch of disk to it, right? So if you have and then you can actually create multiple of such volumes in the over a single cStor pool. So it's like when we have the storage pool climb, and it's converted into the storage pool, that is when the cStor pool is created. So here is where it is, the second slide again, I went back. So at that point of time, the cStor pool is created, and once you have the PVC, and then the PV is created for it, then we have this cStor volume replicas created. We call them as cStor volume replicas. So now, without getting into how this gets created or other details, like now I'll get into like what actually this cStor pool consists of, so that it can actually does the storage for it, like how it stores the data into the thing. So cStor pool is nothing but it's a container, and we have a binary running in it. We call it as a ZREPL. And so basically, now what is this ZREPL all about? Right? So ZREPL is, as the name says, basically it is a ZFS replica, ZFS replication. So so ZFS is something which is like there in the field for many years, and proven for its data consistency and integrity and feature-rich things. So the idea was like, how about using this ZFS and bring it back to the user space, right? So, and we call it as like UZFS, which I can be taken as a micro ZFS. U stands for micro, and again is a user space ZFS. So this ZREPL is made out of is a binary which is made out of this UZFS. The concept, UZFS is the libraries basically, which are made out of the ZFS on Linux. And I'll take this as a discussion session. Basically, if anyone have any questions feel free to interrupt. Any questions till now, by any chance? Okay, I take the next one. So now, what is this UZFS, right? As I mentioned, it is like a ZFS online next thing, and we try to bring it up to the user space. But how do we do that? So there is a DMU layer in ZFS, right? So which is actually um, the point where it have like multiple DM libraries having multiple APIs to create the objects, and it um, allows to write data into the, so that is the entry point for anything to go into the next level of ZFS. In ZFS, actually, once you is like a lot of layers. It's considered the SPA layer, it considered the VDAV layer, and then we have depends on the operating system, the GM layers, and then the drivers comes into picture, which actually runs on the Linux of the kernel part. So um, so now the one which you're using now is the DMU layer which you're using. And again, when going to the disk, instead of using the driver directly calls, we have something called as libIO in the model. So that is where it allows us to run in user space and write in the user space. So we have a DMU layer of ZFS. That's what we use in the user space, and we have libIO in the user space, which will write data to the underlying disk from the user space itself. Basically, again, yeah, through the actors, not through the. It doesn't. I mean, um, it doesn't use the driver directly, but it goes to the actors and then reach the kernel and then final the disk. Hope it makes fine now till now. So and so finally we saw that this UZFS is a library set of libraries which will allow us to create a pool. Basically, given a bunch of disks to it, it will create a pool, the storage pool, and it's like a kind of logical entity, and then it allows us to create it have APIs to allow us to create some of the objects also on which we can write our data. So those are the logical volumes. We call it as logical volumes, and then on which we can write the data. So this data will be coming from the target. Right? So that's how the APIs are provided, the initial APIs which are required. But also, we, for the sake of performance, we have the write-ahead logging, the intent logs will be written. So that as well moved into the user space now. And we have to replay them once if there is any of the power cycles of the pod or the container. So this is how the UZFS right now provides us. In terms of the terminology which we use now, this logical pool entity of the pool is called a cStor pool, and then the block volume, the logical volumes which you create inside the JREPL or cStor volume replica. That's what we usually refer to in the in our YAMLs and CRDs. So now, once we know how to create them, and we want to see how to configure them. Basically, how can we tell to this JREPL or the UZFS to create for me to create a pool or to create the logical volume, right? So, so how do we do that? So basically, we have already the working ones in the ZFS and Linux have something called as ZFS and Zpool. These are CLI binaries, so which can be used to connect to the ZFS of the kernel mode actually. But that works through um, the IACTL model, in the sense like ZFS and Zpool CLI binaries. What they do is they send some IACTLs to they do a lot of processing user space, like given a bunch of disks to these CLI commands or the pool name or attributes to it. It does a lot of checks first, and then it sends IACTLs to the ZFS, which is in the kernel mode. Right. So now our UZFS is in the user space, so they can't connect. each other. So that's the reason ZFS and Zpool binaries won't work with the UZFS which we have now. Then how do we want to do that? So the requirements for us to have is like we do not have a huge amount of code, and it should be easy to maintain. And you don't want to deviate too much from the upstream because you want to be basically keeping live and keep in sync with them, and get new features from the upstreams and contribute back. And then we have and we want to configure it also, right? So what are the options that we have? One way we can think of is like our REST API server, right? So in the in the JRPL binary, we can create some REST API server on which we can keep getting the request. Okay, these are the bunch of disks, and then you execute. I mean, you create me a folder of it. So that can be a kind of request which it can get, right? And there will be like this is a pool name and give me the volume creator out of it. So these are the kind of API we can write. API server which we can write. Any questions till now? Good.
So, just one thing.
Yeah.
You mentioned REST API server,
Yes.
and there are some things going on to write a gRPC server. How are they related?
I think the layer at which we will be writing the basically the one which gets and what is the amount of work it have to do. So we have to. I mean, what I meant is like the ZFS and Zpool binaries. They do a lot of work before even doing these IACTals. So and now we want to bypass these ZFS and Zpool binaries directly and give it into the REST API server. Yeah, it can be the gRPC server or the REST API server. But whatever these ZFS, Zpool binaries do the work, so that have to be done by this gRPC server as well, or the REST API server. So that will cause enormous amount of work to be done inside our inside. I mean, basically to be written and need to be maintained, and moreover, the amount of years of stability which went into those CLI binaries and kind of constraints they add, that will again take time to get to the same stability levels. Was that answered your question, Kiran?
So right, Vita. So if we go ahead with embedding, I was thinking we'll go with gRPC because in the target side we're going with gRPC, just to keep it uniform. But that's the thought process. But yeah, I think I understand what you're saying.
Yeah. So the requirements that we have says that we want to have a less amount of code and easy to maintain and other things like that. So that, yeah, if we don't have other option, we can do that same thing. But and then we just thought of is like something called as IACTL redirection, or you can say it as overriding IACTLs into something else in the ZFS and Zpool CLI binaries. So what is it actually, right? So what we are having is the ZFS and the Zpool binaries. They are left as it is, in the sense like not much of the code except the calls which they do, the IACTL calls which they do the kernel, that are replaced or that are overwritten with the hash if left to our the UZFS code, right? So what it does is instead of writing to the kernel, instead of doing IACTL to the kernel, it tries to Unix domain the socket. So basically the JRPL is binary which is listening on this Unix domain socket. So if you see the previous the kernel version, this ZFS and Zpool binaries talk to the ZFS and Linux, the kernel version. Only thing is it comes to the actual path. So now what we done is like, okay, so which means that the JRPL code is also having the entire thing that kernel can do. Only thing is it can't take the IACTLs. So what we done is like we have a listener created that is a Unix domain socket, and then to which the IACTLs we have a format created for the IACTLs with instead of actors, we'll write a different format on the wire. Basically, it's on the Unix domain socket that will be read by this ZRPL code, basically the ZFS code, and executes the data and basically the functions or APIs. It's similar to actual handling in the user space, and then send back the data to the ZFS and Zpool binaries. Either it can be success or it can be failure, or it can be like some stats or that kind of details. So when we say example Zpool, Zpool create and then the pool name, and we have a bunch of this given to it. As part of this command, the CLI binary does a lot of work. As part of that, that is no change in it, and it does IACTLs. So instead of doing that IACTL, we write to the Unix domain socket, and that is handled in the UZFS code of the ZRPL, the libraries of ZRPL, and served back. So the path goes, the command gets executed without any too much of code change, and also at the same time we don't deviate from upstream too much, but yeah, there will be a decent amount of changes still. The stability is all are maintained as it is. So this is the approach which we followed for configuring the ZRPL. But I mean, who will be doing these commands in the current OpenEBS architecture is, so we have cStor pool MGMT, that is another container which is in the same pod along with cStor pool. So these two actually running in the same pod, and this Unix domain socket which is like a shared among these two pods, and then the ZFS and Zpool binaries which are in the pool management command are triggered by the gRPC server. The server which is in the pool management. So that will trigger this ZPool ZFS binaries, and that will talk to the ZRPL, and that is how the configuration is done. So the pool or volumes are created in this manner. So, and if these two pods are not able to communicate, like whether we say the Unix domain socket is broken or kind of cases, so that's when our CLI commands will fail. And so to get that working, we have this same mount point given to both the pods, both the containers of the same pod. That's how they get a same Unix domain socket, the file which is used for the Unix domain socket, and then they will communicate. This is one place where we need to look at in case if some CLIs are not working. So now the configuration is done, but how to do a read and write into the UZFS, right? So what it means is, like the normal ZFS, it provides you a device. When you create a logical volume, and then you have a device created over it, over which applications can write the data or read the data from. But that again works only for the kernel. We don't have it in user space, that kind of a the device creations, and also being it in the user space, and that extra another overhead to add if we need to do the same again there. And so how do you want to do that? So, and also the requirements again is we want to have less code and easy to maintain, and such kind of things. So we have like multiple options, like you want to create from user space itself some device and then try to turn it back into our code. So we have a lot of can have multiple options, but these are our requirements. Those first three are like standard or constant, we can say, like we don't want to deviate, and we have to have less code and easy to maintain. And now we want to write into the logical volume. So here one thought process was like the layer DMU layer is there, which allows you to write the data into that. So we want to write another layer which actually have a taking data from the target and writing into this API server, the DMU API calls, the basically use API library calls. Okay, so we have a the protocol, or we say like the target when it tries to contact to the JRPL in terms of a data read or write or some operation to be done. So those are the API server, or instead of the API, I would say some listener or server created the JRPL binary to which it connects and it reads the data, and then we have to write into the UZFS block volume from the DMV layer, whatever the libraries which we created, UZFS libraries. From there we have to write into the, it goes into the ZFS and then into the libyio calls and then into the disk finally. So now JRPL, if you see, we thought like it consists of UZFS, and now it also consists of the this protocol layer which need to communicate with the target, right? So how does it look? Just as simple as this. So we have this JRPL binary, and then we have a layer above that. There's a layer in JRPL, the top layer, which reads from ISTZT and writes the ISTZT, and then it does this. So we there is a protocol defined, like this is a header format, and these opcodes, and then the length of the data. So and then we have like 10 opcodes: read, write, unmap, snapshot, create, rebuild, like a lot of other things. So and registering like data, open the connection, and such kind of things. So those are the protocol layer things, and then the UZFS code will come in and then takes the data and write into the disk. So this is the flow of the IO. In terms of reaching to the JRPL binary. So, but basically, if you see, there are two lines of different colors. One is of, basically, what are those, which means that they are different, right? So what we do is in the first time when the replica comes up, it tries to connect to the controller IP, right? So which means that replica here is JRPL is a cStor pool. It consists of cStor pool, and then it has a lot of volumes inside it, and each volume can be associated with different target. So when this JRPL binary comes up, the cStor pools gets loaded, and then the volume replicas, the cStor, the logical volumes will be loaded, and then it will tell that it have to connect to all these targets. And when we connect to this target, that's called as a management connection. And then when this is done, and ISTZT, the target responds back, and then it forms a data connection to the target forms data connection to the replica, and on which the data will be sent, read or write IOs. Any questions? No. I'm done with the presentation. Any more clarity? So this presentation I just keeping in view of 20 to 30 minutes taken the content, but I know there will be a lot of other clarity would be required. So if anyone have anything else, I can try to answer it.
Vida, is it possible to just show the repositories where the code is hosted? Any pointers like that?
Perfect. Yeah. So github.com/OpenEBS is our the repo, and the projects we have is a ZFS, the one which I was talking about till now, the cStor replica, right? So I talked about cStor pool and cStor volume replica, but cStor replica is never actually came to fruition either. cStor replica is a mix of all of them. I mean, basically, it's like a pod which is running and having cStor pool inside it, and then the cStor volume replica. These are logical entities inside it. So the code for that is ZFS, is the one, OpenEBS/ZFS. So .7 release is the branch, and the target code is at ISTCT, OpenEBS/ISTCT. So the part of the code which talks to the replicas is in this the replication.c and datacount.c. So these are the in src directory. Okay, and in ISTCT, the branch we should use is replication branch. This is a branch, and in this replication.c and datacount.c are the ones which talk about which communicates with the replica code. And similarly in ZFS, we have the lib directory. And then we have the libzrepl. This is the one which we have created for this replica protocol, basically the one which talks to the target. So that code is inside this zrepl, lib/libzrepl. And the UZFS things are inside libzpool and libzfs. So that's code locations. And there is another thing called as SPL. This is another dependency required by ZFS itself. So this we don't have a need to change till now. This is provides supporting libraries for the ZFS. That's that answer you, Kiran. Anything else?
Yes, Sudha. Thank you.